Hello and welcome to tonight's stream, the Christmas Eve stream. So I'm going to be doing the last section of chapter 3. This is 3.10, and this is Book of Proof, 3rd edition by Richard Hammock. The download is in the video description. Get the book. It's a very good book, and you will be able to see the answers in the back, so you'll be able to know if I'm getting it correct before I do. Anyways, I'm going to do the reading, then I'm going to do the questions. All right. 3.10, combinatorial proof. Combinatorial proof is a method of proving two different expressions are equal by showing they are both answers to the same counting question. We already used combinatorial proof without calling it combinatorial proof in proving Pascal's formula, which is n plus 1 over k okay. On page 90, there we argued that the left-hand side of n plus 1 over choose k is by definition the number of k-element subsets of the set S with the cardinality equaling n plus 1. But the right-hand side also gives the number of k-element subset of S because such a subset either contains 0 or does not. We can make any k-element subset of S that contains 0 by starting with 0 and selecting k minus 1 other elements from the sets 1, 2 through n in n over k minus 1 ways. We can make any k-element subset that does not contain 0 by selecting k-elements from the set 1 through n. And there are n choose k ways to do this. So this is number of k-element subsets. So it's like singletons, doubletons, tripletons, so forth, of S. Okay. And then this is going to be number of k element subsets of S with 0 and number of k element subsets of S without 0. Okay? So, here we go. Now, we're going to use the combinatorial proof to show that n choose k is equal to n over n minus k. Okay, so by the way, if this sounds a lot like weird and unintuitive, it kind of is. It's hard to get a grasp on this concept, but we'll work our way through it. Okay, so we have prove n choose k is equal to n over n minus k. First, by definition, if k is less than 0 or k is greater than n, both sides are 0, thus equal. So, when we defined what the range of k can be, if k is less than 0 we can't have -1 subsets, and we can't have bigger subsets than the length of the set. Those are multi-sets that we did last time. In this, we can't. Or k is greater than. A multi-set allows repetition of elements. A subset does not allow repetition of elements. Then k is equal to 0, which is equal to k is equal to 0. Sorry, that's not k is equal to 0. Sorry. Okay. No, -1. Sets, no. Subsets greater than the full set. Okay. So we can assume for the rest of the proof, we are working with a range of k that is greater than or equal to 0 and less than or equal to n. Okay, so let's see here. So to derive it, so let's see here. We're trying to prove that the two are equivalent. All right, so let's just do this. We're going to say with n over n minus k. And that we can expand this out to n factorial over n. So in this case, it's going to be k factorial over n minus k factorial, but because of what we have here, it expands out to n minus k factorial over n minus k factorial. So so this, you could think of this as being k. So that's why it says n minus k, that's factorial. So in effect, this is k factorial over n minus k factorial. We just redefined the k as being n minus k. Basically, that's what's going on here. The additional, now, let's simplify this. So n factorial. So now we are going to go with the n minus k factorial. We're keeping that. Now, when we have an n minus, what happens is, look, taking our n minus onto n and plus k. So then we just took off the parenthesis, and then I expanded the minus across to the end. So the two n's cancel, and we're left with the k. So we got k factorial. And then afterwards, we're going to say n factorial over. Now we're just going to put it in our normal order that we're used to, n factorial with k factorial over n minus k factorial. And we could package that back up into n, choose k. So that's the proof. Okay, so basically, so we proved that these two are the same. We just did that. And if you don't understand, I'm just going to walk you back through it again. The bottom, we're defining k as being, and the k portion of it as now equal to the n minus k. That's what we defined it as. So now, then we proceed as if it was k, right? We're just going to write in n minus k everywhere we normally would write k. So in the next part, the n becomes n factorial, and then the rest of the formula, as we're used to when we expand, is k factorial over n minus k factorial. So the k factorial is now n minus k factorial, because that's what we define k as. And then the n minus k is now n minus k factorial. Now, expanding this further out, or simplifying it, I should say, the n minus k factorial remains, and then the expanding the negative into the n minus k, we now have the n minus n plus k. The two n's cancel, so we're left with a k factorial. So our n minus k and our k kind of swap places, but since it's multiplying them out, it'll still give us the same result. In the last portion, we simply put them back into their usual spots, and then we fold it back up. So, and of course, this formula right here, we should be used to it by now. We've been doing this to death already. So we've basically repackaged it back, and therefore we've shown the equivalence of these two up here. These two are equivalent. All right. And that's how a proof works. Okay. Next example, prove we have n sigma. So we're gonna, the sum from k to n of n over k squared is equal to 2n over n for any positive integer n. Integer n. So basically what they're saying is, so with the k is our count here. So we have n choose 0 squared plus n choose 1 squared plus n choose 2 squared plus dot 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 plus n choose n squared, and we sum, the sigma means summation, the 2n over n. So yeah, that's what we're saying. Now, how we actually prove this? Well, in this case, we can pick an n. So remember, it ranges from n to n. Let's choose n is equal to 4. So it's going to say 4 choose 0 squared plus 4 choose 1 squared plus 4 choose 2 squared plus 4 choose 3 squared plus 4 choose 4 squared. So if we did all that, that's going to add up to 4 choose, wait a minute, is that right? All right, it's 2n. So that's going to be, so that would add up to 8 choose 4. At least that's what it should, because it's 2n. And the way we would do this All right, and let's just find out if that adds up. If we have, so then we have, this is choose 0 is 1, 4 choose 1 is 4, and then 4 choose 1, 4 choose 4. There we go. This should be 6, 4, 1. I believe that's the order of it. Let me just check the next one. 4 and squared, of course. Squared, 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 squared. Well, let's see here. 4 factorial over, we're doing a 4 choose 2. 2 factorial, 2 factorial. So that's going to be over 24 over 4, so that's 6. Yes, so that's correct. And 4 choose 3, so that's going to be 3 factorial, 1 factorial over 4 factorial, so that's going to be 4 over 1, which is 4. Okay, so yeah, it adds up. Now, if we were to add up the numbers, so we have, and then if we did 8 choose 4, 8 choose 4, 8 factorial over 4 factorial, 4 factorial, comes out to 8 times 7 times 6 is 5 times 4 factorial over 4 factorial, and then 4 factorial expands out to 24. 24. So then we're going to scratch these. Scratch that. That's 3. 2. 7 times 5 is 35. I believe that's 70. Okay. So then, and then, so does this add up to 70? So we have 16 plus 16 plus 36 plus 2. Okay, 16 32 plus 2. That's 66. Hang on a minute. Hold on a minute. So we have 36 plus 32, 68 plus 2. That's right, 70. Okay, good. So that does add up. So then, because we have here, this is 36 plus 16 plus 1 plus 16 plus 1, which is 70. Okay, so yeah, that works. All right, and then let me just read this question one more time. Okay, so now we are going to use a combinatorial proof. First, so this was just like a demonstration. Technically, showing one example works does not count as a proof. It could only be a proof if you're proving the opposite. So if you're doing a proof by contradiction, where someone gives you a statement and all you have to do is find one counterexample, then, because when you have a proof, it's like for all cases of a certain type, and if you find a type or a case of that type where that does not hold, therefore the proof is disproven. So that's called the proof by contradiction. It's actually one of the easier forms of doing proofs, because all you have to do is just figuring out a way to disprove something. by showing the opposite. But you can do a million examples. That doesn't prove anything. I mean, you can show that it holds for a certain thing, and you can show that there's a pattern that develops, but that doesn't guarantee that it's going to hold forever. So that example by itself is not a proof, generally speaking, unless it's a proof by contradiction. So we're going to use a combinatorial proof here. We're going to go with sigma. So the summation between k choose 0 up to n of the formula n choose k squared gives you the resulting sum of 2n over n. Okay. Right, and all right, so basically this right here, so we're going to say this, we're going to work our way through this. 2n over n is a number of ways to select n from a set S that has 2n elements. So this is going to be n things. So the way k we've been using basically. From a set S that has 2n elements. Okay. So now what we're going to do is we're going to define S further as the union of A and B, and where the size of A is equal to n, and the size of B, the cardinality of B, is also equal to n, and there is no intersection between them. Okay, so we just defined A and B. Now, okay, and then we're going to say for any fixed k, k, with our usual k definition, with 0, k is going to be greater than or equal to 0, or less than or equal to n. We can select n things from S by taking, so remember, it's technically, it's more than just k because it is n. So we're going to have to say taking things from A and n minus k things from B, because remember, S is a combination of both A and B, for a total specific for total of k plus n minus k, which is equal to n things. So the k is from A, the n minus k is from B, and together they give us n. All right? By the multiplication principle, we get, so, and now we're going to use our choosing option. So we have n choose k. So remember, we're taking k from n things, right? And then we're also doing this times n minus k. Okay. from S. So basically, it's going to be like this. If we're going to go from, we're going to take n 0, and this is from A, and this is going to be n minus 0 from B, because whenever we're subtracting k from n, plus n over, choose 1 from A, and then n minus 1 from B. We can't have any overlap, so we're going to say n choose 2 over n minus 2 from A from B, plus plus n over n 0 from A from B. Okay, so basically that's how we did it. Now, so then, but remember, here's a trick. Remember in the previous time, we established, this is why the previous is important. And if we were doing a full proof, we can demonstrate how this is equal to this. The n choose n minus k is equal to n choose k. They're equivalent. So really what we're doing, really, is this. We're going n choose 0, n choose 0, plus n choose 1, n choose 1, plus n choose 2, n choose 2, plus n choose n choose n. And of course, if we were to add this up, this is going to be squared plus n1 squared plus n2 squared plus plus n choose n squared, which is the equivalent of our, we're going to sum it up, we're going to do our sigma notation here. K is equal from, we're going to range from 0 to n. So sigma means we're going to sum up, that's what the sigma sign is, from 0, that's our starting summation, for where k is equal to 0, and it's going to range to k equals to n. K equals 0 is right there. K goes to n is right there. Okay? And sigma means we're going to add them all up. And this is the formula. So we just take that formula that we've been doing from n choose k, and then we're going to be squared. And this is equivalent to doing 2n over n, like that, basically. Let me see here then. And remember, our n, the way we defined it. By the way, if you're thinking that it's a little funky with what's going on with our k, our k's over here subtract out, so it's n is equal to n. So our k's will always add up to our n's, okay? And then the n squared is the same thing as saying 2n. So this n squared is, remember, you're not squaring the items you're choosing, you're squaring the top. So the 2n is also equivalent to saying n squared. In this case, because it's going to be n times n, either way. Okay, I know, brain melty, this stuff is hard to really grapple with, but yeah, it works. At least when I'm doing it, it kind of makes sense to me, but I know the first time it was just completely impenetrable. When I first encountered these ideas. Okay, now, be on the lookout for opportunities to use combinatorial proof and watch for it in your readings outside of this course. Also try some of the exercises below. Sometimes it takes some creative thinking and false starts before you hit an idea that works. But once you find the solution, it usually is remarkably simple. All right. Now, right away, they're warning us that, hey, this is not going to be easy. So that's okay. All right. Use combinatorial proof to solve the following problems. You may assume the variables m and k, p are non-negative integers. All right. So now a lot of these, if you don't get it, just look up the answer, because doing proofs, combinatorial proofs, is hard. It's just in general, doing proofs is hard. So there's no guarantee that you're just going to be able to just crank them out. It's a little different than all the other stuff we've been doing. Now we finally made it. This is once we get through these questions, we actually go into part 2 where it starts doing proofs. This technically already is proofs, but show that 1 of n minus 0 plus 2 of n minus 1 plus 3 of n minus 2 plus 4 n minus 3 plus plus n minus 1 square times 2 plus n minus 0 to the first is equal to n plus 2 over 3. Okay, so I gotta think about this for a minute here. All right. So what I'm gonna do probably, I'm gonna have to ponder these for a while and work on them, and then figure out if I'm doing this right or wrong. But I'm not going to be able to crank these out quickly. So what I'm probably going to do is just stop the video and do a part 2, depending upon how well I understand them. And then, I'll give them a try, check my answers. But I want to be able to understand them so that when I do the video, I could explain them in a way that works. Because it might take me a couple hours to really work through these, and I don't want the video to just be like long periods of silence. So I'm going to end the video here, and I'll do the question and answers in a separate video. All right, join me for that.